Today we're going to talk about exponential decay. So exponential decay happens when a quantity decreases by the same factor over equal intervals of time. So here's the formula for exponential decay. So the exponential decay formula is the following. We have y equals a times the parentheses 1 minus r close parentheses raised to the t power. So what do all these little parts mean? Well, y is our final amount. That's the amount that we're going to have at the end of whatever we are working on trying to figure our total amount. The a value is our initial amount. So whatever we start with. Okay. The rate. Rate is called the decay rate. It is always how much we are decreasing as a percent, and it's always put in as a decimal. Now, the other piece here, this 1 minus r, I'm just going to put this up here. Sometimes we are asked for the 1 minus r. That is actually called the decay factor. It's kind of basically telling us what are we maintaining each time we go forward. 1 representing 100% minus the rate we are decaying, so maybe 10%. So the decay factor would be 90%, meaning we're holding on to 90% each year that goes by. We'll talk more about that as we kind of go, but 1 minus r is called the decay factor, which is different than the decay rate. Rate is saying how much are we changing each year. Decay factor is kind of holding on to what we had minus what we are losing each year. And T stands for time, usually in years. Notice here when we talked about our exponential growth, the value inside the parentheses is always greater than 1. For exponential decay, the value is always going to be less than 1. And again, that becomes from the growth factor. When we had a 1 plus r, the decay factor is a 1 minus r. Again, the 1 representing 100% as a decimal, and then the rate is either going up for growth or in this case going down from that 100% for decay. So let's look at a few examples here. Identifying exponential growth or decay. Determine whether the table represents exponential growth function, a decay function, or neither. Well, what I want to look at is how are x's changing and y's changing. Well, if I look at my x's over here, we can see that we have a nice steady plus 1. So it's important to see that we're changing by something steady. So when we look at the y values, we don't see a nice plus number. But what we do see, hopefully, is something where we would look at and say 270 divided by 3 is 90, 90 divided by 3 is 30, 30 divided by 3 is 10. We don't refer to our decay factor as dividing by. So what we want to think about is that that is the same thing, though, as times 1/3 and times 1/3. We always refer to this as multiplication, not as division. Okay, so x increases. We'll do a little arrow for x increases by 1. The y's are multiplied by 1/3. This is exponential decay. We're multiplying by a factor that is less than 1 over and over and over again, dropping our values as we go. That would be exponential decay. So for the second one, again, notice on the x's, we are climbing by a nice steady number of 2's this time. Doesn't always have to be 1's. We're climbing by 2's. When I look at this next one, I see first maybe a plus 7. I don't see a multiplying an easy one. Second one I can definitely now see plus 7. And we see something that is changing when we're having an adding or subtracting for each of the x's and the y's. That brings us back to thinking slope. So this is actually neither exponential growth or decay. This would be a linear equation. Okay, we need to see something that is multiplying on the y's. So next I want to talk about the last one. We are going to see again, if I look at my x's, I see plus 1, plus 1, plus 1. Okay, so that's so far so good. And now when I look at my y's, I see plus 5, but then it jumps to 10, and then it jumps to 20, so I think I might go back to look at my multiplications, and I see times 2, times 2, times 2. And what we said was if our value inside the parentheses is bigger than 1, we're growing from the smaller x values to the larger x values, and we're growing by a number times a number bigger than 1. This would be exponential growth. It has a common number that we are multiplying over and over and over again. So next we want to talk about interpreting the exponential decay function. This function, p equals 4,870 times 0.94 to the t, representing the population p of a town. So the p is our population after t number of years. So by what percent does the population decrease each year? So when we're looking at how much are we decreasing each year, that's basically trying to find out what our R value is, or our decay rate. So we're looking for the decay rate. So to find the decay rate, I'm going to focus on the decay factor. So remember, the decay factor is basically telling us what we're holding on to. 1 representing 100% of the population minus some amount we're changing each year, or the R value. Well, we know from the function that the whole entire decay factor is this 0.94, which is basically the same thing as saying 1 minus R. Well, to solve this simple equation, I would probably consider adding R to both sides to get R plus 0.94 equals 1. Subtract my 0.94. And my R equals 0.06. Now 0.06 is our rate. However, our rate is always as a decimal. So to get the percent, which is what we were asking for, is simply turning 0.06 into a decimal, into a percent. So we get 6% decay each year. So for the second one, we have a function. We're looking at the amount of coral reef that is there after t years. Again, what is the percent that the area is decreasing each year? So again, I'm going to focus on my decay factor. So 1 minus is going to tell me, 1 minus the 9/10 is going to tell me how much we dropped by. So if I look at the 1/10, that is going to be the rate. So we dropped by 10% decrease. Again, just keep reminding yourself, the 1 represents the 100%, then we are taking away some other percent to get to the decay factor. So we lost 10%. So next we want to talk about how one of these functions work where we were to maybe make a graph, and we want to see how we use the calculator, but how we can figure out a function for a situation. So the value of a car is $21,500. It's losing 12% of value each year. As you may or may not know, when you buy a car, as soon as you start driving it, the value starts going down. As things are being used, as tires get worn, as things hit your car, as just everything happens to it, you spill something in the car, things just happen and your value starts going down. So when you buy a car, we call this depreciation. So to write this function, we're going to call y over here. They asked us to call y the value. The a, remember, is going to be our initial amount. So when we go in to buy it and it's sitting there on the lot all by itself, it is $21,500. Then we always have the 1 minus the rate that we are dropping. Well, we are losing 12%. Remember, 12% always goes in as a decimal, so we have to change it by moving it over 2 places to the left. And we want to leave this t so that you can say to me, well, I want to know what's the value in 3 years, and I can plug it in. Or I want to know the value in 4 years, and I can plug it in. So this right here is the model that we're talking about. We can fine-tune it a little bit better by actually doing 1 minus the 0.12 to get 21,500 times 0.88 to the t. So now we want to graph this. Okay, so a couple of things. We're going to want to talk about how we can make a table. We want to use the calculators, so we can certainly do that. And then we want to show it on a graph. So I'm going to come over here and draw my line. And we're going to put in some points. Our x's, I don't know what that is. Our x's are really our t's, and the y's, remember, are representing the value. So when I plug in a 0, remember our 0 exponent basically means that 0.88 becomes a 1. So at 0 time, meaning we haven't taken it anywhere and it's still sitting there, is worth 21,500. When I put in 1 year, again, I would do my exponent first, use my calculator, and it is now 18,920. At year 2, it is now 16,649.60 for 60 cents. When I plug in 3 years, I'm going to get 14,651.65 cents. Year 4 is 12,893.45, and 5 is going to be 11,346.24. Now, obviously, you can tell that this is going to be a difficult table to try to graph. We would certainly have a graphing calculator that we could potentially use. This is a tough one to kind of graph because we're never going to find a scale that we're going to be able to put all of these in and be able to make a nice, easy, clean graph. We're going to do the best we can. So what I'm going to do down here on my x-axis is we're going to call that our years, and we're going to go every other. So we're going to go every half year. And we went out to 5. When I look at my next one, the value, which is my y-axis, and our value is in dollars, tricky on this one because we don't have easy numbers to look at. I'm going to probably just focus on 3,000 intervals, basically because we just got to get something close. And really, I'm not doing 3,000, I guess. I'm really doing 1,500 because I'm going to skip every other one and go 9,000 and then come all the way up. So I would then have 9,000, 12,000, 15, 18, 21,500 is approximately here for my first point. And then I'm just going to kind of get as close as I can. So if this is 21,000, The 18,900 something at 1 year is about there. The 2-year one is going to be, I don't know, approximately in there someplace, 16,600. The 3-year is 14,600, so that one's going to be pretty close to being on the line. And then I would move to the next one at 13,000 roughly. So that one's going to be again a little bit into this area, and 11,346 for year 5 is going to be someplace there. So certainly not a perfect graph, but what you are going to start to notice here, well, it doesn't look it completely on this one, probably because we're not far enough out. We're starting to see a little bit less each time as we go that we are dropping, because as the value gets smaller, and you think about it, we are losing the same percentage over and over again, but that percentage is going to get a little bit smaller as we go. So we don't have a linear function that's happening here. We see something that is kind of just fading a little bit each time, and the difference between each of them is getting a little bit less. As we go further, it would kind of show more and more as we go. So the question is basically asking us, what's the value after 6 years? Well, we certainly could have plugged it into our function, but based on the graph, because that's what they're asking us to look at it as, I would say that 6 years, we would be looking at some place around 10. So I'm going to say about $10,000. So again, once you start using the graphing calculators, it'll be a little bit more accurate. It's something that we will work on, how to show these graphs. Graphs can be a little bit tricky and can be challenging and certainly take some time and effort to work on. But we want to understand how they're working just manually first. We will be using the graphing calculators a lot instead. And we just more importantly want to understand how a exponential growth in the previous section and now exponential decay is working. Just keep in mind that we have a percentage that is changing as a rate. When we have the the exponential growth decay, we have our 1 minus r factor as less than 1, meaning that we are not holding on to 100% each year as we go.